Hi, my name's Stephen, and I'm an aspiring maths teacher at the University of Wollongong. Today I'm going to show you some techniques for simplifying fractions. Now, I'm not so much interested as doing the basic simplifications, as much as developing a technique that we can use for really, really complicated ones. So if you're looking for a video to introduce the basic idea of simplifying fractions, this probably isn't the one. But I will start with a nice easy one. Now, 10 over 24, I know that 2 is a number that goes into 10, and 2 is also a number that goes into 24. So in other words, 10 divided by 2 is a whole number, and 24 divided by 2 is a whole number. Now, 10 is 2 lots of 5, and 24 is 2 lots of 12. So those 2's cancel, and I'm just left with 5 over 12. Now, I could have done 10 over 24 a little bit differently. So this is the technique that we're going to use to work out some really, really hard simplification problems. Now, I can break the number 10 into its prime factors of 2 and 5. And that's what's called a factor tree for 10. Now notice that both 2 and 5 are prime numbers. That means that I can't break down 2 or 5 any further. Let's look at 24. Now, I'm going to take 2 and 12 again. Now, let's think about 12. 12 is 4 times 3. 3 is a prime number, so I can stop there with 3. And 4 is 2 times 2. So that tells me that 10 is 2 times 5. And that's all over 2 times 2 times 2 times 3. So in other words, the only thing that I can cancel is one of those 2's. Now on the top, I now have 1 times 5 because the 2 is cancelled, so when they cancel they turn into a 1. So I'm left with 5 over 2 times 2 times 3 is 12, so it's 12. So the same answer, right? Now that was a little bit more complicated for that one. It was easier just to see that 2 would go into both of those. But as we'll see, by using the technique of the factor trees, we can actually make a lot of problems a lot simpler. So let's look at another one. 28 divided by 42. All right, let's make some factor trees. Now 28 breaks up into 2 and 14. 14 breaks down into 2 and 7. Now I'll look at 42. 42 breaks down to 2 and 21. And then 21 breaks into 3 and 7. So now I've got the prime factorizations for both 28 and 42, just reading on the bottom rungs of the trees. Now notice how I always went for 2. 2 is always a good choice because it's really easy to just halve things mentally. So if you can see an even number, you can just pick 2. There's nothing wrong with picking it. You'll get to the same answer whether or not you pick 2 or a bigger number. It's just usually 2 is quite nice to work with. So 28 is now 2 times 2 times 7. And 42 is 2 times 3 times 7. So what's going to cancel out on this one? Well, I've got a 2 that I can cancel on the top of the bottom. Now notice that I only did 1 for 1. That's really important. You can't go and cancel 2 2's on the top if you've just got 1 on the bottom. It has to be 1 for 1. And I have a 7 and a 7, so they're going to go away. And what am I left with? Well, I'm just left with 2 on the top and 3 on the bottom. Now, the really, really cool thing about this technique is that when you do it, if you've done it correctly, you shouldn't need to simplify any further once you've broken it down into the prime factors. And that is really, really neat. It makes the working so much easier, particularly on much harder ones. Ooh, now here's a tough one. 116 divided by 328. Well, let's look at 116 first. Now, dividing 116 by 2 I get 58. If I halve 58, I get 29. And then I can't do anything else with 29, can I? Because 29 is a prime number. Now, it's quite tricky to see some of the bigger prime numbers. One thing you can do to check if they're prime is work up factors starting from 2 and see if any of them work. So for example, if I look at 2, 2 doesn't go into 29, 3 doesn't, neither does 4, neither does 5, and neither does 6. Now, I knew to stop at 6. Now, what's the reason that I knew to stop at 6? Well, it has something to do with the Sieve of Eratosthenes. 6 squared is 36. So that tells me that I don't need to look any further because 6 squared is bigger than 29. Cool, now let's break down 328. Alright, well 328, ooh, even halving that one's a bit tough, isn't it? Well, if I halved 300, I'd have 150. And if I halved 28, I'd have 14. So adding those together, 150 plus 14 is 164. All right, I can halve 164, so that would be 2 and 82. I can halve 82 to be 2 and 41. Now, 41, that's prime as well. So working out factors in factors of 41, 2 doesn't work, 3 doesn't work, 4 doesn't work, 5 doesn't work, 6 doesn't work, and 7 doesn't work. Notice that I stopped at 7. So now we can write these down using their prime factorizations. (41). All right, sweet. Now 2 of those 2's are going to go away, aren't they? Cool, so now we're left with 29 on top. And on the bottom, we've got 2 lots of 41. Now, if I refer back to my factor tree, I can see that 2 lots of 41 is 82. And I can write it straight down. All right, 162 over 261. Alrighty, well, that one's a little bit trickier now, isn't it? But as long as we follow the technique, it's actually not too bad. So let's start off by breaking up 162. Now, I know that 162 is 150 plus 12. So I could use 3 there. Another way you could see that 3 is a good one is because the divisibility test by 3 states that if you add all the digits up and they're divisible by 9, then the whole number must be. 1 plus 6 plus 2 is 9. So the whole number must be divisible by 3. Now that breaks into 3 and 54. I can halve 54, so that's nice. 227. 27, thinking back to my 3 times tables, is 3 and 9. And 9 breaks up into 3 and 3. So I've got the prime factors for 162. Now I'll look at 261. Alright, that one's a little bit of a trickier one. But if I use the divisibility test for 3, I can see that the digits add up to 9 again. So I am going to be able to use 3. Now that I know I can use 3, I'm going to think back to my 3 times tables. Now, 8 times 3 was 24. So that means that 80 times 3 is 240. 261 minus 240 is 21. 3 times 7 is 21. So in other words, because 261 is 240 plus 21, if I was to divide 261 by 3, it would be 80 plus 7. Now 87, thinking back to my times tables again, don't really have one on the tables for 87, but I know the digits add up to 15, so 3 is going to work because 3 lots of 5 is 15. All right, 87. Now that's awfully close to 90, and 3 lots of 30 would be 90. So 3 lots of 29, going the next one down, is 87. Now I think 29 is a prime number. Let's check that. 2 doesn't work, 3 doesn't work, 4 doesn't work, 5 doesn't work, and 6 doesn't work. So yeah, 29 is a prime number. So now I can write the whole fraction using my prime factorizations. So 162 is 3 times 2 times 3 times 3. And we've got on the bottom 3 times 3 times 29. Now we can get rid of 2 of the 3's. So what am I left up with on top? Well, I've got 2 lots of 3, which is 6. And on the bottom, I just have 29. And there you have it. So this technique's particularly cool because it means that we can do some really, really complicated ones, but they're actually not too bad. If you have any more questions, feel free to email me if you're one of my students. You have my email. Otherwise, feel free to leave a comment.